Yeah, thank you. And I'm going to be looking at sort of applications of metagradients, particularly the form of meta-learning for finding useful predictive input features for reinforcement learners. So I'm going to start with my motivation. I'm really interested in agents that learn continuously for a never-ending lifetime. So I'm really interested in single agents that learn from their own subjective stream of experience. So if we're looking at this diagram up here, the world is big, it's much larger than the agent is, and the agent can't know everything about that world, but through a small aperture of observations that it receives from the world, it can observe and learn about this large, massive environment that it's in. And the agent is larger than its observations, that is, it can learn to model things about the world through this small aperture. And it's continuously learning from this single stream of experience. So in this sense, I'm kind of departing from many of the talks today in that maybe there's no contexts or explicit tasks, and maybe there's no testing and training regimes. The agent is doing it live. And so in particular, this talk is focused on how agents can learn to find predictive input features. So I'm going to start with a brief discussion, it's already been touched on already, about the reinforcement learning problem and how generalized value functions can be used as predictive input features to augment an agent's observation stream. I'm going to introduce a method of learning what predictions an agent might choose to use, and I'm going to leave you with a taster. I'm going to pick a particular result from the paper that we're sharing at this conference, and you can find more in our paper. So again, the motivation of this, a lifelong learning agent will need to learn about many different aspects of its environment. And this might actually be, for a subtle reason, common sense for a lot of folks. There are policy gradient methods, but oftentimes when we're doing reinforcement learning, an agent will participate in learning a subtask. It will learn the value of a given state before it learns the optimal policy. And so in a sense, that's kind of learning to model the world in a way. And we can expand upon that and think about model-based agents that are learning to explicitly model their world. And we can use predictive input features as a way to model the world through an agent's subjective experience. And as per sort of the topic of this conference, for large environments, for real world environments especially, we as designers cannot know what will be most important to the agent for decision making ahead of time. There might be non-stationarity, as Yelena was talking about, or simply the world might be something that we cannot model. Certainly physics hasn't solved the modeling problem of the real world yet. So can an agent independently choose what to pick to learn about through a meta-learning process? So again, the reinforcement learning problem, we have an agent that takes actions that affect the world that it's in, and it observes the world and receives a reward from the environment. And its goal is to maximize the expected future discounted sum of reward. For long-term decision-making, for the reasons that we recently discussed, it can be useful to learn about many different aspects of the environment in addition to just estimating the value of a state. So one way for an agent to continuously learn about its world is by learning many value functions. And you might be familiar with value functions for estimating expected reward, but we can generalize that to any observation that is available to an agent or any stimulus that's available to the agent. So using the same incremental online learning methods that we know and love, notably TD methods, you can estimate the future discounted sum of any future stimulus that's available to an agent. Think about how we anticipate different stimuli on a day-to-day basis as we're interacting with our world. So without getting too far into the weeds of general value functions, there are 3 parameters that I want you to keep in your mind. The first being the policy, which is the behavior that an agent is engaged in when it's making this prediction, or the behavior that the prediction is conditioned on. The second is the cumulant, the signal of interest that is actually being anticipated by a GVF. And then the third is the discount, the horizon, or the temporal timescale that the prediction is being made over. So again, we can estimate these value functions online and incrementally so they're well suited to this lifelong learning regime that we're interested in. So how does an agent choose what predictions to learn or use the predictions that it has learned? Well, typically, there's some sort of internal representation the observations are passed through that produces an agent state. Maybe it doesn't describe exactly the state of an MDP if we're doing real world applications or something of that nature, or a partially observable problem, but you get the state from the agent's subjective experience. So in this case, what we're doing is we're taking these value estimates, we're taking these GVFs, and we're concatenating the predictions that are made on each time step with the observations that the agent receives from the environment. So we're augmenting the observations that the agent receives with estimates about what it feels the future will be like from its perspective. And this is actually a really rich applied area of reinforcement learning work, surprisingly. Predictive input features are very useful for real-world applications of RL. Going back to 2016, you had bionic limb control interfaces for amputees that are using assistive robotics. You've got industrial laser welding processes that are integrating these GVFs into their control policies. Neural implants for Decerabit cats. Exoskeletons is also a really interesting new line of work, building control interfaces for exoskeletons, and the development of VR assistance for human-machine collaboration on joint action tasks. So there's a wealth of different lines of work that have really benefited from this idea of predictive input features. One limitation, however, from this whole line of work is that in each instance, the predictions were hand-selected by experts with a considerable amount of domain expertise. And I mean, the last lesson of the machine learning revolution was that hand designing kernels was maybe not the final solution for developing machine learning systems, and that letting agents pick what is best for learning is often a better solution. So to that end, we're asking whether or not an agent can independently choose what questions to ask. And we're going to continue along the line that Elena thoughtfully introduced for us, which is talk about meta descent beyond MAML. I'm sure a number of you are familiar with MAML as a meta learning process across tasks, but there's actually a rich line of work beyond MAML in metagradients that goes back to the 90s. So again, determining what predictions to make is an open challenge. There's some recent work that has explored how an agent might randomly select and evaluate GVFs, choosing to keep the ones that have the lowest empirical return error, the ones that are most accurate from the agent's subjective perspective. However, selecting the most accurate GVFs is not the same as selecting the most useful GVFs. So an alternative is to specify metaparameters and enable the agent to learn what to predict based on feedback from its control learning process. And again, metagradient methods have a rich history, starting with step size adaptation with incremental delta bar delta and K1. And people have used it to weight the incoming features in MLPs. There's been work in adapting the return through the discount parameter. And there's been some recent exciting work in modifying auxiliary tasks, what they're about based on metagradient processes, which is very similar in spirit to this work. So in this vein, we're exploring how metagradients can be used to specify what predictive features an agent chooses to learn about. So again, value error drives learning. You have a control agent that receives some observations from the environment. And in our particular case, the observations are concatenated with a set of predictions. Those predictions are parameterized by the cumulant, the policy, and the discount. And instead of handpicking the cumulant, policy, and discount, we're going to parameterize and learn them. Because the value estimates of each GVF are inputs to the control agent's error is dependent on the parameters that specify what these predictions are about, what the agent is choosing to learn about. So we can take the gradient of the control error with respect to these underlying parameters and learn them through stochastic gradient descent. So I'm going to highlight a result from one of the domains that we explored, which was recently introduced. It's called Frost Hollow. It is a temporally hard control problem. That is, there is a partially observable element of the environment that appears at a random cycle, and the agent has to succeed in avoiding this temporal event over many successive cycles before it even begins to observe reward. So it was originally presented as a domain to explore predictive input features, particularly in relation to agent, and human agent joint action problems. And in this case, human agents, or rather human designers, were able to select GVFs in order to solve the problem, or in order to enable an agent to solve the problem. So we're asking, can an agent do the same incrementally and online? And to do that, we are going to show you the cumulant learned. So what should the agent predict? Over on the left-hand side, we've got sort of the axis of the heat map, which is the input feature that an agent is weighting for the cumulant. A combination of inputs and weights produces the cumulant. The cumulant changes over the duration of the entire experiment. So we're going to show you how each contribution of each feature varies over time. And then finally, we go from cool colors, which describe little importance or little contribution to the cumulant, to yellow colors, which are highly weighted. And you can see that they start sort of equally and randomly distributed, and over time, one GVF cumulant really dominates, or one feature really dominates the specification of the cumulant, which is interesting because the feature chosen in the originating paper by the human designers, Butcher et al. 2022, was feature number 7. And instead, the agent learned to select a different cumulant as its signal of interest. This is especially interesting because the agent, in this case, that was meta-learning what predictions to select, outperformed the human-picked baseline pretty substantially. So in this case, letting the agent learn its own predictions enabled it to pick something that was better suited to all of the different factors that contribute to the learnability. So that's the function approximator, the other parameters, the environment itself. So wrapping things up, agents were able to find questions that were useful as predictive input features, and that enabled them to solve a partially observable decision-making task. And interestingly, we found through 2 different environments in our paper that the questions that were chosen by the agent, the predictive features, were often different from the ones originally proposed by experts. So concluding thoughts, taking the gradient through the whole architecture is sort of the inspiration for this work. What should an agent know about? An agent should know about whatever is useful for it in solving a task. And what is useful to an agent? What helps the agent minimize its perceived error? So again, an agent was able to learn incrementally and online what predictions to make in order to support decision making. And this really unlocks a whole area of applied reinforcement learning work that, as of yet, required a great deal of domain expertise and intervention by designers. And with that, if there's any questions, I'd be happy to answer, and you can find a link to our paper above.